All right, so yesterday we finished up talking about E1 chemistry, at least the overview of it. We said when you do E1 chemistry, there's a few things you have to pay attention to. The first is your starting material. You have to have a good leaving group. And after it forms off, you need to form a relatively stable carbocation. Remember, anytime you have a carbocation too, you have to watch out for rearrangements. And then in the next step, your base, which is typically going to be a weak base, is going to pluck off one of those beta protons. We said beta protons in this case don't need to be anticoplanar, they just need to be next to that carbocation, and that will give you your E1 elimination product. We said you don't want to use a strong base because we said strong bases always favor E2, they never favor E1. So typically the base that's used is going to be an alcohol or something incredibly weak. All right, there is also one other thing to watch out for. And you guys actually saw this in lab, is if you have heat plus a primary or secondary alcohol plus a concentrated strong acid. So for example, in lab we use cyclohexanol and we use sulfuric acid and heat. We were actually able to do E1 elimination. And why is that? Yeah, exactly. We saw in lab, in this situation, the first step will always be protonation of your alcohol. So I'll just use sulfuric acid, which we saw in lab. We don't have a good leaving group right now, so just like with SN1 chemistry, we need to protonate this first. Once we protonate this, we've got a really, really good leaving group. At this point, our leaving group can fall off. This can give us a secondary carbocation. Is this going to rearrange at all? Nope, there's no way we can rearrange it into a more stable carbocation. And then at this point, your water is a really, really weak base. It can grab one of these protons, clamp down, whoop, give you your alkene, and then regenerate your acid. So when you look at this, the key thing is your strong acid, in this case, is usually catalytic. And what does it mean when it's catalytic? Yeah, it regenerates itself during the reaction. You can see we put acid in, but we kicked acid off in the end, so we don't need a full one-to-one stoichiometric equivalent. We only need a little bit in order for this to work. Why are we adding heat to this reaction? Because it's elimination and we want it to favor that over SN1 chemistry. And then we also need to have a primary or secondary alcohol because the carbocation that we're going through needs to be relatively stable. What do you think happens? Oh, sorry, this should be a tertiary or secondary alcohol. I got ahead on my notes. What happens if we have a primary alcohol? Do you think it's still going to be E1? Yeah, if we have a primary alcohol, it's thought to go through E2 rather than E1, and it takes a really high temperature, so it's not very common. Typically, you only see E1, and you typically only see dehydrations with tertiary or secondary alcohol, so you do need to watch out for that. Okay, so now what we need to do is practice a little bit. So let's do a couple practice problems. Whoop. All right, so let's do this one. And we're just going to use a catalytic acid, and rather than writing out full sulfuric acid, I'll just abbreviate it as H+. And then I'll write catalytic, and then the diamond signal down here, delta, means heat. So this is likely going to be an E1 elimination reaction. We know it's E1 because it's a secondary substrate. We've got catalytic acid and heat. So I'll give you guys a minute to do this, but I want you to determine which product or products you think you'll get from this reaction. I'll get us started too. I'll do the easy steps first. So first step we know will be protonation of our alcohol. And that's because the alcohol at first is not a good leaving group. Now we've converted it into a good leaving group. What should I do next? Kick off our leaving group. Okay, so we've got our carbocation. Does anybody want to help me with the next step? Rearrangement, right? Right now we've got a secondary carbocation. We know that that's not too stable. So are we going to do a hydride shift, a methyl shift? What do you guys think we should do? Hydride shift. And the reason being, we've got a hydrogen right next door, where if we move this entire hydrogen over to that carbocation, now we've got a tertiary carbocation, right? We know that that's energetically very favorable. All right, so now we've done the rearrangement. We now need to identify our beta protons. So I'm going to go ahead and draw in our beta protons using some blue arrows here. So I've got beta protons off of this methyl group. Got beta protons off of the other methyl group. Are those any different from one another? No, it doesn't really matter which of those we grab. We also have 2 beta protons coming off here. And if you remember, we kicked off water. So water is going to be floating around. Which beta proton do you guys want to go after first? Okay, so let's go after the ones on the right first. So when we do this, we can say, all right, we're going to end up with both methyl groups that were there in the same place. We've now got a double bond here, and we've got this right here. This is the most substituted alkene we can get, so this we immediately know will be our major product. Are there any other products you think we might get? Yeah, we could also go after one of these beta protons, clamp down. So we could say, hey, this could be a minor product as well. So we would get 2 different products out of this reaction. Do we have to worry about cis or trans isomers here? So for example, up here, is it possible to get both cis and trans? It'd be the same, right? So there's no point drawing it twice. You don't have to do that. Same thing with the bottom one. You can pluck protons off that top methyl group, but it gives you the exact same product. It doesn't really change anything here. So for this reaction, we get 2 different products. The top one we said would be major, bottom one would be minor. Is this reaction stereospecific, stereoselective, or regioselective? Yeah, so this reaction is regioselective. If you remember, regioselective reactions give you a mixture of products that are constitutional isomers where one is major and the other one's minor. So in this case, the major one we can see is the tri-substituted alkene. Does that make sense? You guys want to try a harder one? All right. This was one I got from the book. Depending on what edition you have, I think this is 2nd edition, problem 81. And they say propose a mechanism and it looks pretty complicated, but it's not too bad. Got this bicyclic ring system. You've got an alcohol coming off that far end. You're going to treat this with catalytic acid and heat. And when all's said and done, you still have 2 rings, but the double bonds have moved around. And your final product looks like this. So let's try to draw a mechanism from how we can get from our starting material all the way to our product. I think this was actually an old exam problem. How many of you want to work on this as a class? Raise your hand. All right, so let's do this as a class. First step is going to be what? Protonation, just like we saw before. So kind of repetitive. Got a double bond here. Now we'll have a protonated alcohol, which is a great leaving group. Still have these methyl groups hanging off. What's the next step? Leaving group falls off. Okay, so we'll still have both ring systems. We've got a secondary carbocation right now. Is there any way to improve this? Yeah, in this case, we'd probably want to do a methyl shift, right? If we did a hydride shift from the bottom carbon, we'd just be going secondary to secondary. So let's take one of these methyl groups from the top corner and move it down. All right, so now we've got a secondary to a tertiary carbocation. Is there any way to rearrange this to an even more stable carbocation? What's better than tertiary? Resonance, right? So let's try rearranging it a bit until we get resonance. We know we've got this blue proton that's assumed to be coming off that top carbon. So when we move this over, whoops, now we should have a tertiary carbon with resonance. In fact, let's draw both resonance structures out for this. And we know with resonance structures, you can move a pi bond over like that. Actually, sorry, I'm going to condense space here. Which would give us our double bond right there and our cation right there. So we know this is possible because this is tertiary with resonance. Does that make sense? All right. If we look at our final product, we're almost there. What do you think the last step's going to be? Yeah, we have to deprotonate a beta proton. We need to get a double bond right there. That means the beta protons we need to select must be coming off of this lower position here, right? Okay. Does it matter if they're anticoplanar or not? No, because it's an E1 elimination. So all we're going to do in this one is grab one of these beta protons, clamp down, and will give us our final product right there. So some of these are pretty tricky. You do have to pay very careful attention to resonance and rearrangement, things like that, similar to with SN1 chemistry. Does that make sense? All right, so what I want you guys to do now is to pull out that pod that I forgot to print off for you yesterday. We'll do it in class as a small group activity, so you can check it with your friends, neighbors, colleagues, loved ones, anyone that's around, and see if you can come up with all 3 different products. Yep, as long as you do it, you get hopefully full credit, right? Because we're going to go over the key. All right, let's try doing this as a class. So for this problem, I immediately told you it's E1. That gives you a big hint for the first step. What's the first step got to be? Kick off the leaving group. Okay, so I'll go ahead, kick off this bromine. All right, so now we've got both 5-membered rings still fused together. Oh, that's not a 5-membered ring. There we go. Got a carbocation right there. It's a tertiary carbocation. That's pretty good, but what else does it have? Resonance. So let's draw both resonance structures. Excuse me. We know we can take this pi bond and move it up there. That would give us both resonance structures. Whoops, let's clean this up a little. Sorry, just don't like my drawing right now. Okay, so we've got a positive charge that's delocalized across two different carbon atoms. All right, next step that I always do is identify my beta protons. So I'm going to draw those in as green beta protons. I've got beta protons up here. Those are the protons that are next door to that carbocation. If we look at the bottom resonance structure, we also have a couple other beta protons, right? Are there any beta protons right there? No. Nope. That carbon's got a full octet already, but we've got beta protons right there. So we know we've got 3 different sets of beta protons that we can potentially pluck off to give us our product. So what I'm going to do is show 3 different products. We know we're going to get 2 from that resonance structure, and we're going to get 1 from this one. We know water in this case is our weak base. So 3 different reaction pathways. The top reaction, we know we could have grabbed one of these beta protons. That would give us a double bond right there and there, right? So that would be one potential product. The second potential product could have been to grab one of those beta protons, clamp down. This looks pretty similar. But now we've got a double bond right here and another one right there. Does that make sense? And then last but not least, we could have a beta proton grab one of these, clamp down, whoa, and we could get our third potential product. How many of you guys were able to get all 3 of those? Looks like that. Yep.
Why don't, on the first structure, why don't you have like a double bond between those 2 shapes?
Double bond between both ring systems?
Yeah.
Because we're only looking at the top resonance structure for those first 2 reactions, right? And so for that upper resonance structure, we only have the beta protons on the top, and we don't have a localized pi bond in between those 2 central carbons.
Oh, I didn't look at it correctly.
Yep. So in this case, there's 3 different products. It'd be really tough to determine which one's major or minor, but this is a good example of seeing resonance in action. Does anybody know what we'd call this type of system when you have 2 alkenes? It's not a normal -ene suffix. What would it have as its suffix in the name? It'd be a diene, right? We won't get into naming some of these more complicated bicyclic dienes, but it's important to remember anytime you have more than 1 alkene, you want to name it a di, tri, or tetraene as needed. Does that make sense? All right, don't forget to turn this in. These are freebie points, so you can use that to help your pod grade a little bit. So hand them in the front before you head out today. All right, we do have about 10 more minutes. So I wanted to introduce you guys to the most confusing part of the chapter. How to distinguish between SN1, SN2, E1, and E2 is really tricky. So I like to break it down first. I don't like it when students memorize this because it's really easy to forget things you memorize. I want you guys to understand why certain reactions work and why other ones don't. So the first one we'll do is if you've got a good nucleophile, which is a bad base, that would be something like a halide, so chloride, bromide, iodide. What were some other ones that we saw that were good nucleophiles but bad bases? So halogens, and there was one other group, sulfur groups, right? So I'll call them sulfur nukes. Okay? So we've got one whole class of reactions that only reacts with good nucleophiles. And what I like to do is break this down for the substrate. So you can have a methyl substrate that has a leaving group on there. You can have a primary. You can have a secondary. You can have a tertiary. What happens, for example, if you've got, something like this and you treat it with a strong nucleophile?
Oh,
Will that be SN1, SN2, E1, or E2?
SN2.
SN2, exactly. So for this one, we'd say, all right, this has definitely got to be an SN2 because we've got a strong nucleophile. It can definitely do SN2 chemistry. What about with primary carbons? Will that do SN1, SN2? SN2, right? Why doesn't it do SN1 for primary carbocations? Or, oh, I gave it away. Why doesn't it do SN2 for primary carbons? Carbocations are too unstable, right? What about secondary substrates? They can do either SN1 or SN2. What's a good way of predicting whether or not it's going to be SN1 or SN2? Yeah, what you could do is maybe look at solvent. Or reaction rates. So if you've got a polar aprotic solvent, is that going to favor SN2 or SN1? SN2, exactly. If it's a polar protic solvent, that tends to favor SN1. If you're still stuck, check the reaction rate. If you double the concentration of your nucleophile and the rate doubles, is that SN2 or SN1? It would be SN2, exactly. All right, and then last but not least, we've got tertiary carbons. Will that do SN2 or SN1? Only SN1. So it's important to remember those basic SN1, SN2 trends. I know a lot of this is review, but it's important to remember that SN2 is more likely going this way. And then we said SN1 is more likely going the other way. So just a little bit of review of last chapter. All right, let's go on to what happens if you've got a good base that isn't a good nucleophile. So a good base, but a bad nucleophile. What are some examples of good bases that aren't good nucleophiles? What was that one? The big one? Yep. The big one. This guy. Terbutoxide. It's too big to be a good nucleophile. What were some other ones? So we said bulky nucleophiles are crummy base, or sorry, bulky bases are crummy nucleophiles. What was another type? What was that?
Surface chemistry bases.
Surface chemistry bases. So something like sodium hydride, potassium hydride, etc. What were the special ones? DBN and DBU. All of these are really good bases, but really bad nucleophiles. So same sort of thing. What I like to do is take a look at it and say, all right, what if we've got a methyl group that has a leaving group on it? What if we've got a primary? What if we've got a secondary? What if we've got a tertiary? All right, so what happens if we have a methyl group that has a leaving group on it? What sort of reaction will it do, or will it do no reaction? So we can't do SN2. It's not a good nucleophile. Strong bases, we know, like to do E2, but what's the problem with the methyl group that has a leaving group coming off of it?
It's a very stable carbocation.
You have no beta protons, right? Ah, so this one would do no reaction because there are no beta protons. All right, what happens if you have a primary carbon with the leaving group on it? It would definitely do E2. We just saw that this last chapter. All right, what about secondary carbons? Strong base? E2. What about a tertiary carbon? E2. So a little bit redundant. Anytime you've got a strong base and you've got beta protons around, E2 is something you always need to consider, right? All right, these are all going to be E2. Which one's going to be the fastest reaction, primary, secondary, or tertiary, between all of these E2s? Yeah, tertiary. We said typically the more substituted alkenes are going to proceed at a faster rate, so this would be the faster E2. Does that make sense? All right, now the tricky thing becomes, well, what happens if you have a good nucleophile that's also a good base, meaning it can do either or? All right, so same sort of thing. We'll say, all right, we've got methyl here, we've got primary here, we've got secondary, and we've got tertiary. All right, if we've got a good nucleophile that's a good base, what do you think is going to happen if we have a methyl group with the leaving group on it? Just SN2. We saw it can't do E2 at all, so this one would be SN2 only. All right, let's kind of change gears and look at the tertiary one. Will that be SN2, E2, E1? What do you guys think?
E2.
It's got to be E2. We know it can't do SN2 because that backside's too hindered. So this one would be E2 only. So we can kind of see a trend here, right? The more accessible the backside is, the more likely it is that substitution will occur. But we know that E2 reactions actually prefer to have more substituted carbons. Okay, so now let's take a look at the primary one. We're going to get a mixture out of this potentially, but what do you think is going to be our major product?
SN2.
SN2? So I'd say, all right, SN2 is going to be major. What do you think could be a minor product?
E2.
E2 minor. We know that E2 reactions tend to be a little sluggish on primary carbon, so it's going to go fairly slow. SN2, on the other hand, that's a pretty accessible backside, so that's definitely going to be a major product. All right, following this same trend, what do you think is going to be major and minor for secondary carbons?
E2 major, SN2 minor.
Yeah, so it'd be E2 major, SN2 minor. That backside now is getting pretty dang cramped. That's going to really slow down the SN2 reaction, but we know E2 doesn't really care. In fact, it's relatively stable doing that E2 reaction, so it would be E2 major, SN2 minor. All right. Last but not least, we've got bad base, bad nucleophile. Same sort of thing. We've got methyl, primary, secondary, tertiary. The bad bases and bad nucleophiles tend to be neutral molecules, so this would be things like alcohols. They don't have a negative charge on them, so they're not very nucleophilic, they're not very basic. All right, if we look at these ones, do you think anything's going to happen with the methyl group that has a leaving group on it?
Not really.
Yeah, so I'd say too unstable as carbocation. What about primary carbons?
Probably favor E1.
Yeah, in this case, it's probably still not very likely. We know primary carbocations are super unstable, as well as methyl groups. Secondary carbons, we've seen that occasionally, like on the dehydration of cyclohexanol. So this one can actually do E1 or SN1. It's oftentimes a mix. And same thing with tertiary. It can do either E1 or SN1. What do you think is going to favor E1 over SN1? So let's say we only want elimination, we don't want substitution. What could we maybe do to the reaction to favor E1 and SN1? Or sorry, this should say SN1 here. What was that?
Said crank the heat.
Crank up the heat, right? So high heat favors E1. And then the other thing we said is catalytic acid plus alcohols that are either tertiary or secondary will favor E1. SN1 is typically observed at lower temperatures just because elimination doesn't have enough energy to occur. However, it's usually observed as a mixture still of E1 and SN1. However, you can't distinguish which one's major and minor. Does that make sense? All right, so your newest pod isn't actually due tomorrow, the one I have up here. It's due on Thursday, the last day of class. It's worth 20 points. It's a more difficult pod, so what I would recommend is try to get started on it earlier rather than later. And we'll actually do some practice problems in class tomorrow, too, to help you get a little bit more guidance for how to problem solve those.